Um, Hello everyone, I'm Paloma, and this video is part of MFCS 2020. I will present the paper called Algorithms for the Rainbow Vertex Coloring Problem on Graph Classes. This is a joint work with Erik Jan van Leeuwen and Marieke van der Weggen from Utrecht University. So I will start telling you what exactly is a rainbow coloring. So in this presentation, I will always be talking about vertex colorings. So instead of keep saying rainbow vertex coloring, I will omit the word vertex. So we start with a vertex colored graph, and by what we can see here in the picture, we already know that we're not necessarily talking about a proper coloring. So two adjacent vertices might have the same color in this setting. And a rainbow path between two vertices is a path such that all the internal vertices received distinct colors. So for instance, this path here that is highlighted is a rainbow path between X and Y. Note that the colors of the endpoints don't really matter. So they might be the same, and they might be the same as a color that appears in the internal vertices. So the definition of rainbow path is only about the internal vertices of the path. Then a rainbow coloring is a coloring such that for every pair of vertices of the graph, there exists a rainbow path between them. So, and a stronger variation of this concept is that of a strong rainbow coloring. And it is when I also require these rainbow paths to be shortest paths. So for instance, this coloring that we see in the picture is a rainbow coloring. So we can check that for every pair of vertices, I can find a rainbow path between them. However, it's not a strong rainbow coloring, as the unique shortest path between X and Y has two internal vertices that received the same color. But for instance, if I change the color of one of the vertices to blue, then now I have a strong rainbow coloring for the graph. So from the definition, we can already see that every rainbow coloring or strong rainbow coloring will always need at least diameter of G minus 1 colors, since this is the number of internal vertices in some shortest path in the graph. So the parameters associated with these colorings are what we call the rainbow vertex coloring number and the strong rainbow vertex coloring number that are denoted like this. And they are the minimum number of colors that we need to rainbow color or strong rainbow color a graph. So it's also easy to see that they satisfy this relation here, since every strong rainbow coloring is also a rainbow coloring. So this problem was first defined actually in terms of edge-colored graphs, and relatively recently in 2008. And the vertex variant was defined 2 years after by Krivelevich and Euster. And yeah, in this talk, I will only be talking about the vertex variant. So I will never be saying the words vertex and edge too many times when I talk about the coloring itself. Okay, and knowing the parameters, then we of course have the decision problems associated with them. So we're given a graph and an integer, and we want to know if this graph has a rainbow coloring with at most k colors, and similarly for the strong variant. So these two problems have been widely studied, but I put here the results that are more related with graph classes since this is the focus of our work here. So it's known that both of them are NP-complete for a fixed K, and they remain NP-complete on split graphs and bipartite apex graphs. So apex is a graph that has one vertex whose removal leads to a planar graph. And there are some polynomial time cases. So for instance, for unit interval graphs, bipartite permutation and block graphs, and it's also known that the problem is polynomial time solvable on planar graphs, but in this case for fixed K. And the case of interval graphs is interesting as well, since it's known that as polynomial time solvable the rainbow vertex coloring problem, but the strong variant, the complexity is unknown still. So in this work, we will extend this landscape of what is known about the complexity of these two problems in graph classes. So in particular, we will consider the class of permutation graphs, and we will show that actually every permutation graph can be rainbow vertex colored with diameter of G minus 1 colors. And we will also consider the class of powers of trees. And these are chordal graphs. We previously saw that the problem is NP complete restricted to chordal graphs. And here we can find a subclass for which the problem can be solved efficiently. So they will always be colorable with diameter of G minus 1 or diameter of G many colors, and we can decide in polynomial time which is the case. Finally, we will consider also the class of split strongly chordal graphs. So we saw previously also that the problem is NP complete restricted to split graphs, and but in this particular case we can solve it. And the number of colors will always be either diameter of G minus 1 or the number of cut vertices of the graph. So note that the strongly chordal graphs, they are chordal graphs without induced suns. So a sun is a graph that is formed by a clique and an independent set that contains vertices that are adjacent to two vertices of the clique. And so for instance, here we have the example of the 3 sun and here the 4 sun. And what we actually show in contrast with this last result is that both problems are actually NP complete if we consider split graphs, but we only restrict a finite number of suns. So split strongly chordal graphs are the split graphs without no induced sun, without induced suns. And if you actually forbid any finite family instead, then the problem is NP complete. So we say this is an observation because we actually use the same reduction as Hegernes and others used for to show that the problem is NP complete on split graphs. We just, instead of starting from coloring, we start from a more restricted version of coloring that leads to a split graph with no induced suns. So, but the proof itself is the same. In this presentation, I will focus on the result for permutation graphs, and I want to show you more or less what we did and what are the main ideas behind it. So let's take a look at what motivated us. So One thing that can help us to give upper bounds on the number of colors that we need to rainbow color a graph is the presence of a connected dominating set. And why is that? Well, if I have a connected dominating set in a graph, I can just color the vertices of this dominating set with pairwise distinct colors. And to the rest of the graph, I can give like arbitrary colors. And whenever I want to go from a vertex U to a vertex V, so it's clear that if a pair of vertices is contained in the dominating set, then there is a rainbow path between them since we have a connected dominating set. And if I want to go from a vertex that is outside this connected dominating set to another vertex, for instance, like U and V here in the picture, then I can just jump to the dominating set, find a path, and jump back to the vertex V. And like this, I'm sure to have a rainbow path between any pair of vertices of the graph. So one thing we could think of, remember, I'm sorry, so before I proceed, just to notice one important thing. This gives an upper bound for the rainbow coloring number, but not for the strong variant, as we have no guarantees that jumping to the dominating set will give us a shortest path. So two vertices might be connected by different shortest paths, and then we would have to really take care of giving colors to all the vertices and not only for the ones that are in this connected dominating set. Okay, so remember that diameter of G minus 1 is a lower bound for our parameter. So what we could try to do is to look at a connected dominating set that would put us maybe close to this lower bound. For instance, what if we consider a graph class that has dominating shortest paths, meaning that every graph in this graph class has a shortest path between a pair of vertices that is dominating. That sounds a bit restrictive, but this is the case for many widely studied graph classes, like for instance, interval graphs, permutation graphs, or AT3 graphs. So let's see what would happen in this case. So we have our dominating shortest path, and we give different colors to all the vertices. So in this case, we get diameter of G plus 1 colors. Note that this is 2 more than what we would like to spend according to the lower bound. So we would like to suppress 2 colors in there and to be able to still use our core idea of getting from a vertex that is outside this dominating set, jumping to the dominating set, walking in the dominating set, and then reach another vertex that I want. I could only suppress the colors possibly of the endpoints of the path. But this is a problem since these vertices might have neighbors outside the dominating set that are dominated only by them. And in this case, if we want to go from vertices that are here to any other vertex of the graph using our previous strategy, then we would need to define well a color for V, so that because V will be an internal vertex of this path. So as I previously mentioned, our main result is for permutation graphs, in which we show that this lower bound is actually always enough. And what we will do is to see how we can fix this problem with the endpoints of the dominating path. So first, so that we're all on the same page, I would like to define a permutation graph properly. So um, a segment intersection model for a graph is a model like it's drawn here in this picture, in which we have two parallel lines and we have some segments that connect these two lines. And the intersection graph of this model is a graph that has one vertex associated with each segment. So for instance, I use the colors here to show who is associated with which segment. And two vertices are adjacent if the corresponding segments intersect. So a graph is a permutation graph if it's the intersection graph of some permutation model like this. So for our algorithm, we will be often using the intersection model only instead of the picture of the graph itself. So, and then in this model, given a segment, for instance, this one corresponding to the vertex V, we call this point the top and this point the bottom. And yeah, okay, let's proceed. So the key to solve this problem is actually, instead of using one dominating path in this graph, is to actually use two of them at the same time. And we will define which two according to the intersection model of the graph. So we start with this vertex P1 to define the first path, which we will call P. And this is the vertex that has the smallest top. So we can see like the points here with, we can compare who is small and who is larger according to whether a point is to the left of the other or to the right of the other. So the second vertex of this path will be among all those that intersect the segment of P1 to be the one with the largest top, like here. And now, among all the ones that intersect P2, we'll take the one with the largest bottom. And so it goes until we cannot choose one anymore. And the second path will be defined in a similar way, but now we start with the vertex that has the smallest bottom. And again, the second one will be among those intersecting that one, the one that has the largest bottom, and then the third one will be the one having the largest top, and so on. And notice that here, the last two vertices of the path are actually the same. They just appear in opposite orders in the path, but they're the same. Okay, so what will we do? The first thing we will do is to take these two vertices, P1 and Q1, and we will run a BFS rooted in these vertices. So we will have a picture like this in the case of the vertex P. So we call the levels of the BFS L1, L2 until LD. And note that the path that was P1 to PD appears here in such a way that PI belongs to level LI. And the most important property that this path will have is that the vertex Pi will be adjacent to all the vertices contained in Li plus 1. And this really helps us to color the graph For instance, if one, and we will do the same with the vertex with the path Q. So we will run a BFS that will be rooted in Q1, and we will have a similar picture. So if either one of the paths has diameter of G many vertices, then we are good, because we can color P1, P2 until PD minus 1 with distinct colors. And whenever I have two vertices and I want to go from one to the other, then I will just jump to the previous PI that is adjacent to everybody, and I walk on this path, and then I reach any vertex that I want. So this will be a rainbow vertex coloring for the graph. So the tricky part is when both paths actually have diameter of G plus 1 vertices. Because in this case, remember, I want to color with diameter of G minus 1 colors, which means that if I want to give colors to the vertices of this path, then two vertices will need to have colors that already appeared previously. So then this strategy that I previously used is not so straightforward anymore, since this path that is very easy to see is not a rainbow path anymore. But what we will show is that actually, if we color, we will keep the vertices of the level LD plus 1 colored with the same color as P1. And we will color the vertices of the level LD this time with the same color as P2. And we will show that this coloring actually works. So in every level, I colored actually all the vertices now with the same color as the PI contained in level LI. Okay, so let's quickly see how I find the rainbow paths. So I will need to use the vertices of Q as well. So the first thing we prove is that actually when I look at the path Q, I have Q1 in L2 and Q2 in L3 and so on until QD minus 1. We're sure it is in LD minus 1. And notice that in this case, the problem is always when I am in a vertex, when my pair of vertices that I want to find a rainbow path between, one of the vertices is in L2 and the other one is in LD, right? Otherwise, that previous straightforward idea of jumping to the path P still works. Since if the vertex instead is in LD minus 1, then I just jump to P3, and from there I can reach any other vertex with a rainbow path. So our main issue is when we have a vertex in L2 and a vertex in LD. So what we show is first that we saw that QD minus 1 was in the level LD minus 1. And what we prove next is that actually PD is the same as QD minus 1 and PD minus 1 is the same as QD, as we previously saw that it happened in that example that I drew. The last two vertices of the path were the same but appearing in different order. And we also show some properties regarding the adjacencies of a vertex that is in LD and a vertex that is in L2. And now we will use these properties to find rainbow paths. So for instance, suppose we have the vertex U and this vertex is not adjacent to P2. Note that if it is and I want to reach a vertex DV in LD, then I can just jump to this path again, and it will be a rainbow path using the vertices of P. So then I'm in the case that these are not adjacent. So if V is adjacent to QD minus 1, then we're good, because we actually show that if I have a vertex of L2 that is not adjacent to P2, as we see here, then this vertex has to be adjacent to Q1 or to Q2. So if it's adjacent to Q2, I have this rainbow path, and if it's adjacent to Q1, I have this other rainbow path. So in this case, we're good. So now we assume that V is not adjacent to QD minus 1. But then in this case, as we can see here, V has to be adjacent to QD minus 1. And now, if U is adjacent to Q2, then again, I have a rainbow path like this. So the issue is when U is not adjacent to Q2 and instead is adjacent only to Q1. As you can see, this path is far too long. So this won't really help us. And in this case, we will have to look at shortest paths connecting U and V. And with some work, we're able to prove that such shortest paths have at most one vertex in each level, except for L2, in which the shortest path will have two vertices, U and one more. But then since U is an endpoint, this will not be a problem. So this will be a rainbow path between U and V. But this takes a lot more work, and I will not explain the details here. So to conclude, it would be nice, of course, to know the complexity of rainbow vertex coloring in AT3 graphs and in diametral path graphs, since permutation graphs are subclasses of these two, and we believe the problem should also be polynomial time solvable. It would, of course, be nice to see the strong variant of this problem solved for permutation graphs, as we give an algorithm that works only for the normal variant. And as I mentioned, we gave algorithms for powers of trees and split strongly chordal graphs. So both these graph classes are subclasses of strongly chordal graphs. So it would be nice to know what is the complexity of these problems for strongly chordal graphs. Note that for powers of trees, we also don't know the complexity of the strong variant. So yeah, that's why I put the strong variant in parentheses in there. But yeah, these are the main open problems related with what we did. And thank you very much for watching.